Hello, I'm Irini Caldelli, Associate Researcher at the National Technical University of Athens, and I will shortly present a methodology in supporting digital platform which combines a suite of automatic annotation tools with human validation for the semantic enrichment of culture heritage metadata. The work to be presented has been co-funded by the European Commission under the projects Crafted and AI for Culture. Semantic enrichment in our case refers to the process of analyzing textual metadata that describe culture heritage items, for example, their main characteristics, location, creator, etc., so as to link them with URIs, unique reference identifiers, derived from vocabularies or open data sources such as Wikidata, geonames, or the Getty vocabularies. Those terms may represent concepts and attributes such as costume, renaissance, colors, named entities such as persons, locations, and organizations, or chronological periods. Semantic enrichment brings several benefits to online digital collections, making them more easily discoverable and accessible. Firstly, linked data makes the meaning of textual metadata unambiguous. For example, the string Leonardo da Vinci may refer, depending on the context, to the Italian Renaissance polymath or a battleship with the same name. Secondly, linked data allows us to retrieve additional information about a certain entity in an automated way, build connections between different resources, and contextualize them. For example, it allows us to link items tagged with the term armchair with a broader concept of seat, and thus interconnect them with items enriched with the term chair, which is also an instance of seat. Moreover, linked data usually comes with translated labels, thus improving the capabilities for multilingual search. The methodology and supporting platform we have implemented has been applied and evaluated on a set of datasets on crafts heritage, from furniture and jewelry to costumes and clocks collections, coming from various culture heritage organizations, including aggregators, museums, and archives. The methodology and tools have been applied within the common European data space for culture heritage, and in particular in connection with Europeana, allowing the enrichments to be published on the Europeana web portal. Several natural language processing and machine learning technologies can be employed to automate the time-consuming and often mundane process of manual metadata enrichment. The accuracy of the results highly hinges on the available data, and culture heritage metadata pose certain challenges. They often suffer from poor quality and include short textual descriptions with no sufficient context. As a result, machine learning algorithms trained on news articles, for example, may result in many incorrect matches or may miss matches that are relevant in the specific culture heritage context. This means that in some cases, lemmatization and string matching approaches may yield better results than machine learning based algorithms. What's more, even if the automatically detected links are correct, they may be considered undesirable for a certain case study. For example, linking metadata records with terms representing colors may be important for a fashion collection, but it may be irrelevant for a manuscript whose description just happens to mention a certain color. Human inspection and validation is an integral part of the end-to-end semantic enrichment workflow. Since it is a resource-consuming task for large datasets, it has to focus on an appropriately selected sample while making sure that participants have the necessary expertise, depending on the task. Overall, depending on a number of factors, including the text characteristics, its length and language, the vocabulary that we wish to link it to, and the type of entities to detect. For example, do we wish to identify a broad variety of concepts or to limit ourselves to certain domain-specific terms? Depending on all these factors, a different combination of tools and steps is required to achieve the best possible results. The methodology we followed for the semantic enrichment of culture heritage metadata consists of the following high-level steps. The first step concerns the preparatory tasks of aggregating the data and specifying the requirements for the enrichment. For example, which metadata attributes to analyze, which vocabularies to link to, etc. The second step involves the automatic analysis of the textual metadata with aim to derive useful annotations in line with identified requirements. In the third step, humans are solicited to review and validate the automatically generated annotations. And finally, the outcomes of the human validations are analyzed to establish appropriate thresholds for filtering, and the filter annotations are embedded as enrichments to the metadata records. The enriched metadata records are ultimately published to the Europeana platform. This slide provides an overview of the main digital components that support the aforementioned methodology. The central component is Sage, an online linked data management platform developed by our team that combines automatic annotation tools with human validation to streamline and facilitate the workflow of semantic enrichment. The Sage platform has been configured to facilitate the semantic enrichment of culture heritage metadata in particular by offering parameterizable templates that are connected with relevant in-domain vocabularies and knowledge bases. Moreover, Sage interacts with other components within the data space for culture heritage, namely Europeana and Mint, which is a metadata management platform used by several aggregators to prepare and publish the data to Europeana. For data importation, Sage provides parametric input templates to directly import data from Europeana's and Mint's APIs in line with the Europeana data model. The annotation and validation results produced by Sage are exposed to download through an API, which can be used by Mint to collect the results, apply any additional filtering, and publish the enriched datasets back to Europeana. Let me now describe the Sage platform and its capabilities in more detail. Sage provides three main functionalities. First, create linked data content, which can be done by importing data from various existing sources and formats and converting them and storing them as linked data. Second, publish the imported data and thus make them publicly available through several APIs that provide different ways to access them. And third, apply several processing services on the imported data, and in particular, of most interest to the present methodology, data enrichment and validation services. With respect to importing data, Sage allows importing data from several commonly used formats such as XML, CSV, JSON, even semi-structured text files, etc., and from several sources such as REST APIs, relational databases, or even from zip data files that the user uploads. All the data are imported in Sage as linked data using the relevant W3C standards. In fact, the importation process is at the same time a transformation to linked data process. The transformations can be performed either by custom user-defined mappings or predefined parametric data mappings using an RDF mapping language specifically developed for this purpose, which is called D2RML. Each imported data collection in Sage gives rise to a distinct dataset, and datasets can be organized also in catalogs, that is, in groups of datasets. The next step, publication, is a process that makes the imported datasets available for actual use by loading them to an RDF store, that is a database for storing and querying RDF data. It should be pointed out that Sage is not itself an RDF store, so a third-party RDF store must be used that fulfills certain technical requirements. And currently, support for OpenLink Virtuoso and GraphDB is provided. Once a dataset is published, it is available through SparkQL endpoints for querying. The data in a dataset can also be indexed for fast retrieval using a flexible indexing mechanism and made available through appropriate search APIs. Finally, distributions on the datasets can be generated, that is, data dump files available for direct download. Finally, and of most interest to the enrichment methodology, is that Sage includes components that allow the automatic enrichment of the published data. These components are called annotators and are based on external third-party data processing services, which are typically available as REST APIs. Given that automatic enrichment is not perfect, once one or more datasets have been enriched, validation campaigns can be set up to allow humans to go through and inspect the automatically produced annotations, accept or reject them, as well as add new manual annotations as enrichments. After this short general overview, let's focus on the annotator services offered by Sage. Annotators are applied to selected parts of the data, which can be, for example, the set of values of a particular property in a dataset. Annotators should be able to appropriately process that values and return a set of linked data URIs that are somehow relevant to the input data values. Any external data processing service that can provide such enrichments can easily be added to Sage by writing an appropriate service interface. The main annotators currently provided by Sage can be classified into three main categories. First, we have SparkQL annotators, which link a text to external knowledge bases by querying the respective SparkQL endpoint. Some widely used publicly available such endpoints include Wikidata, DBpedia, and the Getty linked data vocabularies. Second, we have nerd annotators that perform named entity recognition and disambiguation text. And finally, we have thesaurus annotators that perform smart string matching in order to link terms in text to a given vocabulary, typically a SCOS-based thesaurus. Next, let's see a typical example of using each annotator type, starting with a SparkQL annotator. SparkQL annotators work better on fields with short identifier texts, like label, person, and location names, and usually the user may have to manipulate first a bit the input data to bring it to a suitable format and then write the appropriate SparkQL query. In this example, shown in the slide, the data imported in Sage have a creator field written in a specific format. Because SparkQL queries typically work with exact string matching, we have to transform the string to the form expected to be found in the external knowledge base as the name of that person. Therefore, we first apply a regular expression, and then by submitting the appropriate query to the Wikidata Sparkle endpoint, we retrieve the respective Wikidata entity. Nerd annotators are more automatic and require less user involvement since they can handle directly any text with no manual intervention, preferably longer text with rich context, which helps the underlying tool derive the correct entities. Typically, nerd annotators first detect named entities like persons, places, organizations in the text, and then try to link these to entities of a knowledge base, like Wikidata, using the context. In the example on the slide, the tool detected three named entities and was able to correctly link them to the respective painting, artists, and institute entities of Wikidata. Examples of nerd-based annotators provided via Sage include the DBpedia Spotlight service, which links text to DBpedia entities, the Wikidata Reconcile annotator, which uses OpenRefine service to link single data values to Wikidata entities, a nerd annotator that makes use of the IDA tool that is trained on news articles and supports several languages, and another pipeline that uses the spaCy library and the multilingual mGenre model for disambiguation for linking with Wikidata. It is the last two nerd annotators we experimented with for the enrichment of the considered crafts collections. The third main category of annotators are thesaurus annotators. Thesaurus annotators link parts of text to the terms of a given vocabulary, employing string matching and other typical NLP techniques like lemmatization. As already mentioned, the vocabularies should in general be SCOS vocabularies and should also be imported to Sage, similarly to other datasets. The matching is done using the labels of the vocabularies terms. In the example on the slide, we see the detection of some materials and colors in the text from a given vocabulary. After datasets have been automatically enriched using one or more annotators, Sage allows humans to check and validate the enrichments as already mentioned. Since at this stage human involvement is required for large datasets, validation can typically take place only on a relatively small sample of the data. The following criteria were used to guide the selection of the annotation sample to be validated so as to ensure representativeness across various parameters. First, the sample should include annotations that appear in a high number of records and thus will have a high impact. Ensure a balanced representation of metadata fields, including fields with varying semantics and expected text length. And we should also take into consideration automatic confidence levels assigned by automatic algorithms, if available, by including annotations with a rather low confidence score, but also sufficient number of annotations with a rather high score. The validation process is organized around validation campaigns. To facilitate the process, the validation is done not on an item per item basis, where an item is an entity in the dataset, but in a bulk validation mode, where identical values, which should have identical enrichments, are grouped and presented to the validator together, sorted by frequency. Let us now see how the methodology was applied on the Crafts heritage collections. The analyzed metadata came in the following languages: Dutch, Italian, French, Greek, English, and Croatian. The following vocabularies were used: the Europeana Fashion Thesaurus, the Art and Architecture Thesaurus, the EU Screen vocabulary on audiovisual heritage, and a SCOS vocabulary on Greek crafts heritage. In total, the SAGE annotators were applied on more than 216K metadata records, giving rise to more than 915K total annotations and more than 549K unique annotations. Unique annotations refer to unique triples of filled textual values, matched substring, and identified URI, while the total annotation count considers all annotations without grouping together identical filled textual values. In other words, counting all times the same annotation defined as a triple may appear in different items. Overall, more than 30K unique annotations referring to more than 15K records were reviewed via SAGE, and of those annotations, more than 23K were accepted and approximately 7K were rejected. Validation feedback was analyzed with the aim of establishing thresholds for annotations that are considered acceptable for publication. To this end, the following metrics have been calculated per dataset, per annotator, and per analyzed metadata field: precision considering only unique annotations, and precision considering all annotations. It should be noted that numbers calculated based on unique annotations are considered more reliable, since the total number is skewed towards textual values that are repeated in multiple items. For the use cases we considered, most human experts did not focus on the manual insertion of new annotations, and the few manually added annotations we collected did not allow us to sufficiently estimate false negatives and thus compute metrics such as recall and the F-score. The overall precision, defined as the number of all accepted automatic annotations produced by SAGE over the number of reviewed automatic annotations, is 0.76, considering unique annotations, and if all annotations are counted in, then the overall precision is 0.82. Precision varied largely depending on the analyzed metadata field, the type of annotator that was used, and the datasets that were analyzed. The minimum and maximum precision reported in the table refer to a per metadata field level. Thesaurus annotators were applied to both longer and shorter fields. Longer fields such as description and title, shorter fields such as format, type, or creator. Often after case-appropriate regular expressions pre-processing, giving rise to generally satisfactory results in both cases. SPARQL queries on Wikidata were used on metadata attributes representing creators and special information. Although in most cases it did not produce a high number of annotations, it scored a high precision. mGenre and IDA-based nerd annotators were applied to description attributes, title attributes, as well as shorter fields, including creator, spatial information, and rights related fields. And they both produce similar results, performing well for short fields, but poorly for longer ones. In the latter case, they both struggled with disambiguation between multiple candidate entities entities, and even when produced as matches that were in principle correct, those were often too generic and thus considered irrelevant by validators. Annotations have been filtered by discarding all annotations rejected by humans while including all explicitly accepted ones, considering a majority vote. For non-reviewed annotations, a threshold based on precision was applied, depending on what was considered acceptable by data providers. For annotators for which an automatic score was produced, we also attempted to plot the logistic regression between the automatic score and the human judgments. However, no correlation was found between the two variables, and therefore automatic scores were not used as factors in the filtering rules. In total, after filtering, about 549,000 annotations have been imported to around 133K records, in line with the respective Europeana data model extension for representing enrichments. All enriched records have been published to the Europeana web portal. And this is an example of how the automatically produced annotations ultimately appear on the Europeana platform. The read, would, and beach word terms that you can see here are all automatic enrichments added by Sage that are visible on the item page on Europeana. There is a special sign that indicates enrichments that were not part of the original metadata, but rather added by partner projects. In case of non-validated annotations, a special indication that these were produced by a software agent is shown. Before concluding, I would like to draw your attention to the AI for Culture platform, which provides access to various tools, datasets, and upskilling material about AI technologies relevant to the culture heritage sector. There, you will be able to find more information about the Sage platform, including a series of video tutorials, a workshop recording, technical details, etc. Thank you for your attention.